Hello, welcome to Binary Hacking, this winter 2021. I'm Ethan Sifferman. I'm a third-year computer engineering major, but I've been playing around with like binary data probably since, I don't know, I was like 11. I would go and like download pirated Pokemon games, and I would like look in the code and be like, wow, like this is so cool. Or I'd like download Pokemon hacks and I'd play hacks of Pokemon games, and I would like try to make my own Pokemon hacks. Granted, like they weren't good at all, so you shouldn't be impressed, but I at least have been fascinated by this stuff since since I was young. So so this class is going to be just a little bit about how binary data is stored, how we can edit binary data, how we can figure out what binary data is. I talked about this a little bit at the IEEE meeting, but I'll just give another quick demonstration. So here I have the actual like file for Super Mario Brothers, and like we can play this game if we wanted. Like here's Super Mario Brothers, and we can just go into this file and we can start editing it. So here is like the entire game just written out in hex. Yeah, so you can see like the entire code of this game, and this seems completely crazy. Like how does anyone decipher anything from this? But that's what we'll be doing in this class. Is we'll be trying to figure out like, okay, so like what is this section right here? It's like, oh, okay, these 3 bytes are associated with like the color of Mario or something, maybe like this section is like all about like the pipe, like what the pipe looks like in Mario. But today all we're going to be looking at is kind of just what binary is and what hex is. Because maybe you haven't even heard of what those terms are. So if we look at these values, so you can see like some of them are like 03, 03, 07, but some of them are like E8. Like what the heck does E8 mean? Is this a number? And if we look here, we can see like 8-bit binary, which just looks like a bunch of zeros and ones, like 90, 0, 02. So in a little bit, we'll be going over like how to actually read this. But first, I want to show you the course website. So this is the class website. I made this in preparation for this class, and it has all of, right here, it has all the lectures, so you can go and click on them once they're available. Currently, we are on lecture 1, and we can scroll down, and you can see, so here's all the required software for this class. And here's a little note about buying Super Mario Brothers. It's illegal to download the ROM file to a game that you do not own. So therefore, here's some links if you want to buy it. So here's some references, and here's my contact information, as well as IEEE contact information. The best way to find me is on Discord. Let's open up lecture 1. So this is what I'm hoping all of you will do by the end of class today. And honestly, if you want to like work ahead, like kind of while I'm lecturing, that's totally fine. Hopefully the lecture will only go on for like 40 minutes or so, so that you'll have plenty of time to do this. But it's pretty simple. It's like download the tools, okay, and like download Super Mario, okay, organize your files, okay, sure, and then complete the exercise. So it's pretty simple. A quick note, you must be on Windows for this class, at least for the Super Mario Brothers portion. Yeah, so you're going to want to get Windows by next week. You don't need it this week, but by next week, you'll need to have Windows. Here's some links for that. And then you go and make sure you download the software. Actually, I want to show you, so I have this section right here about organization. And that's because I'm extremely passionate about keeping my files organized. So if you look, so here are all the classes that I am teaching. Or last quarter, I taught web development, so that's like pretty organized. Yeah, lectures, examples. And then this is like also very organized. So here we can see like the intro unit. So here, I like to keep everything very organized, and it's going to help you so much because these files that we're dealing with can be very, very difficult to figure out like what they are. You may know exactly what the file is when you're editing it, and then you hit save, and then you come back to it a week later, and then it's like, wait, what does that do again? So it's very important for this class. Because you can't really open this file like immediately in like Microsoft Word and like know, this is my essay, blah, blah, this and that. When you open this up in Visual Studio Code or whatever editor you're using, it's very hard to tell, like, okay, what the heck is this? What is this game? What is, I don't even know what's going on here. So it's very important to label all your files and organize them very cleanly so that you don't get mixed up. Okay, that was my little rant on organization. I have a little folder structure if you want to follow that. That's what I'm using. Oh, and I'm going to record all these lectures. I'm currently recording right now, I believe, hopefully. Yeah, and yes. I'm recording, and I'll put them on the class website by probably like the end of the day, each class. So first, we're going to start with a very trivial task. We're going to just count numbers. So start at 0. What's next? 1, 2, 3, 4, 5, 6, 7, 8. Wait a minute, 9. Wait. Okay, I can't remember the number that comes after 9. What comes after 9?
10.
10? Wait, how do we write 10?
Doesn't it?
Write 1 0.
1 0? Well, that's 2 characters. But like, is there a way to write it with just like 1 character?
Say A.
A? What is it? Isn't that a letter? No, I don't know what you're talking about. There's no way you can write 10 as like in just normal everyday sort of math. Like there's no way that we can just like write 10 with like 1 character. So what do? Well, we just kind of like start over. So we go to like back to 0 and then 1, 2. But then what we do is we keep track of like that we kind of like ran out of room. We keep track of how many times we ran out of room by putting this 1 here. So we have this, this 1 that says, okay, so actually we ran out of room right here 1 time. Oh, okay, so let's keep going. So 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. Uh-oh, what happens? Oh, I know. Okay, so we put a 2 here to say that we ran out of space 2 times. And then we put a 0 here. Okay, yeah, so now and then we keep going. So, okay, so, and so if you look, if we like ignore this, all these 1s, it's kind of like, it's all of this like 0 through 9, like repeat. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it keeps repeating. And then here we see like, these could be like 0s, and then it goes 1. And then if we continue this, it would be 2. And if we continue, it would be 3. Now let's see what happens. So if we keep going, now we're at like, I don't know, like 97. We go 98 and 99. Uh-oh, what comes after 99? Oh. Yeah, so what comes after 99? Oh, I know, it's 110, right? Wait, no, that doesn't make any sense. So now all of a sudden we need to add a new whole place to say that, okay, so actually we ran out of room again. So we need to have like another place. So we put a 1 here, and then we put a 0 and then a 0. It's because we like reset these both back to 0. So that's actually what numbers are. That's what counting is. That is how the Arabic symbols work, is you have 0 through 9 that are all periodic. And then you have 0 through 9, which are periodic, but like they change like 10 times slower. And then after that, it's like 100 times slower. Keeps going. All right. Any questions on that? It's kind of just like review from like, kindergarten, but still can be. So yeah, okay, this is considered base 10. And the reason it's considered base 10 or decimal, the reason it's considered base 10 is because there are 10 different numbers we can choose from. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0. So there's 10 different numbers. Now let's consider like maybe like a theoretical like base 9. Okay, so we might have like 1, 2, 3, 4, 5, 6, 7, 8, and then 0. So 9 different numbers that we can choose from. So we could have 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, what's the next number? Wait, why is it 1, 0? Why isn't it 9? Well, it's not 9 because we don't have that number. That number like just doesn't exist because like we're in this imaginary world where we don't have 9. So yeah, we put a 10. And the 10 just means like we've reset the counter back to 0. And the 1 just says, okay, so we overflowed 1 time. Yeah, pretty simple. So then we can go like 1, 1, 1, 2, 1, 3, 1, 4, blah, 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 up to 1, 9, or 1, 8. And then we go to 2, 0, and 2, 1, 2, 2, 2, and dot, 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 until now we have like 8, 6, 8, 7, 8, 8. Uh-oh, what happens? Now 1, 0, 0. That's if we were to just boom, remove 9 from our numbers that we use. Cool. Okay, so now let's consider like a new number system. Let's consider base 3. So base 3. So we have 3 numbers: 0, 1, and 2. Okay, so 0, and then 1, and then 2. Now, what comes next after 2? Can someone help me?
1, 0.
Yeah, 1, 0. Because we don't have a 3, so it kind of like repeats. It just repeats itself, and then we have a 1 here, just to show that like we're on like our first repeat. Okay, yeah. So 0 or 1, 1, 1, 2. And then, we have to repeat again. So now it's 2, 0, 2, 1, 2, 2. And then, 1, 0, 0. And then 1, 0, 1, 1, 0, 2, 1, 1. So yeah, this is what a base 3 counting system would look like. All right, now we are finally ready to talk about binary, which is just 0 or 1. And this is how binary works. It's the same way, same method as like just our normal counting system, except we've just taken all the numbers 2 through 9 and we've just removed them. So we have 0, we have 1, and we ran out of room. Okay, so let's put 1, 0, and 1, 1. We've run out of room again. Okay, so 1, 0, 0. Okay, 1, 0, 1. Okay, 1. Ran out of room. Okay, 1, 1, 1. We've run out of room, but this is like a big one this time. Oh my gosh. There, boom. Okay. Can everyone private message me what the next number is right here? It's not a trick question. I just want to make sure everyone's kind of following along. Yeah, so since there's this 1 here, if we were to add 1 to it, so we can't go to 2. So we have to set this back to 0, but then we set the next place to 1 because the next place like signifies that we've repeated. Yeah, so this would be the next number. All right, wait, okay, now what's the next number after this? Can everyone go and put in the chat now? Nice, yeah, wow, everyone got that. Cool, yeah, so 1, 0, 1, 1. Okay, and now, okay, what's the next number? So it's, cool. Yeah, 1, 1, 0, 0. So that's how binary works. All right, so, and now it kind of sucks to write out binary. So I'm gonna pull out this, this calculator app that Windows gives us, and let's write out a number, let's say like 58, and let's look at it in binary. So this is what it looks like in binary. And generally whenever we write out binary, we keep it in chunks of 4. So, and it's always good to kind of like precede with zeros. And you'll see why we keep it in chunks of 4s in just a second. Okay, let's write out like a really big number. Let's write out like, I don't know, that. Okay, let's look at what it is in binary. Oh my goodness, look how big this number is. Like, okay, so this was whatever, 7 digits, pretty long. But this is like absolutely massive. That's huge. Like if we look at that, like, oh my gosh, how do we even, okay, quickly, like what is this number? Go, put in the chat, like what is this number in decimal? Like that's a dumb question. It is so hard to to decipher what this number is off just by looking at it. However, computers, it's really easy for computers to deal with these numbers. So computers are the ones who use binary. Humans, we don't like binary. That's why we have like decimal. That's why we have like base 10, like 1 through 10, is because that's way easier to read. Binary is really hard to read. But as computer scientists, we have developed a new way to look at binary data, but actually like make sense out of it. And the way we do that is through hexadecimal. So hexadecimal is base 16. And so a few people were talking about it earlier. So let me just write out the numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have A, B, C, D, E, F. So we just add these characters to like the normal numbers. And now, so if we wanted to count, so we would do like 0, 1, 2, 3, ... and then we would go from 8, 9, A, B, C, D, E, F. And then what number do you guys think will come after F? We've like run out of room here.
Would it be 1, 0?
Yeah, it'd be 1, 0. Yeah, so boom, we put 1, 0 here. Okay, cool. And then we can go like 1, 1, 1, 2, 1. 1 3 1 4 dot dot to 1 9, and then 1A, 1B, 1C, 1D, 1E, 1F, and then now 2 0 and 2 1, and you can keep going. And then let's say you got to like 9C, 9D, 9E, 9F, and now it would be A0, A1, A2. Yeah, so this is how you count in hexadecimal. Yeah, if we go like FC, F, FD, FE, FF, it would loop back. So go 1 0 0. And 1 0 1, 1 0 2, 1 0 3, dot dot dot, 1 0 9, A, dot dot, 1 0 D, 1 0 E, 1 0 F, 1 1 0. Yeah, and then if you have like FFF and then +1, yeah, after this. And but so hexadecimal is miraculous and was invented specifically to help write out these massive binary numbers. Because watch what this number is in binary. So if we go to this this chart right here that just maps like decimal to hexadecimal to binary, what we can do if we want to write this out in hexadecimal is we can say like, okay, so what is this number? So this is 5. So we can just have this be 5. Okay, what is this number? So, okay, this is 9. Okay, and what is this number? This is just 1. Okay, what is this number? This is right here, so it's 6. Okay, what is this number? This is just number 5 again. Okay, and what is this number? This is C. Okay. So what's really cool is that we can take this massive binary number and just split it up into these chunks of 4, and we can get its what its representation in hex is. Because if we look at this number and then look at its hex representation, you see, so yeah, 59156C. Cool. And this took very little effort. Now, if we have some super long hex number, or maybe even like a short hex number, now we instantly, just by looking at that, the more practice you gain, you will be able to now get the binary out of it. So yeah, you maybe hand delivered this hexadecimal number, and by me just like giving you this number, now you know this much longer binary number. All right, so yeah, I want to look back at this now. So this is Super Mario Brothers. I'm going to open it up in a hex editor again, so we can see the hex values of it. So 53. We can go and instantly get its binary representation right here. Wow. And here, so you can actually see, so the first 4 bits of this, so first 4 bits of 53 is 0011, and this is 3 in binary. And these 4 bits are 5 in binary. So that's where this 53 comes from. It comes from this binary of 5 and then 3. And yeah, and if we were to convert that to decimal, to like our normal base 10 counting system, 53 would end up being 83. But what we're going to do now is we're going to talk about bitwise operations. Common ways to manipulate binary data is through bitwise operations. So first, let's start out with the AND operation. So AND, you can think of it kind of like a plus sign, like when you say like, oh, like 2 plus 5 equals 7. Except we're doing AND, so it would be, so 1 and 0 equals 0. And 1 and 1 equals 1. And 0 and 0 equals 0. So what the AND says is, given 2 bits, so a bit meaning like either a 0 or 1, if both bits are 1, then return 1. So in other words, like, okay, is this a 1 and is this a 1? Then if so, then give a 1. Cool. Okay, is this a 1 and is this a 1? No, this is a 0. So instead, just return a 0. Okay, is this a 1 and is this a 1? No, neither of them are 1. So just give a 0. Okay, so that's what an AND does. There's also an OR, which is so 0 or 0, 0 or 1, 1 or 0 or 1, 1. So this says if either of them or if both of them, really, like if there exists a 1, then just give a 1. So is this a 1 or is this a 1? No, neither of them are 1s. Okay, is this a 1 or is this a 1? Yes, so give a 1. Okay, is this a 1 or is this a 1? No. Wait, I'm sorry, yes, give a 1. Yeah, because this is a 1. Is this a 1 or is this a 1? Yes, they're both 1s. So this is the AND operation, and this is the OR operation. All right. Okay. Wait. Quick pop quiz. What is I don't know, 1 and okay? Let's do in parentheses 1 and 0 or 0. Go. Excellent. Yeah. Okay. Now, what if I change this to 1 and 1 or 0? And go and direct message me. Yeah, awesome, cool. Okay, what about this? Just it's the same answer. Yeah. Okay. Good. Let's do a slightly harder one. Let's say oh, what is that? Okay, let's think through it. So 1 and 0. So is this a 1 and is this a 1? No. Only one of them is a 1. Okay, so therefore this is a 0. Okay, I'm sorry. Is this a 1 or is this a 1? No, they're both zeros. So therefore 0 or 0 results in 0. Good. Okay, most of you got that. Cool. Okay. Now let's consider not. So not is fairly simple. It's just like not 1 equals 0, and then not 0 equals 1. So it just inverts it. Pretty easy. And then let's do XOR. And XOR is the same as OR, except now when we say that they are both 1, we set that to 0. Cool. So this is XOR. So let's do like a slightly harder one. I'll make this full screen. There we go. Okay. So let's say you have 1 XOR 0, not or 1 and not 0. All right, what is this? All right, let's walk through it. So we have, so not 1 XOR 0. Okay, so this is 1. Then we have OR 1 and 1. So 1 and 1 is just going to be 1. So, and then this ends up being, so just 0 or 1. So this ends up being 1. Yay, okay. Hopefully that's all clear. So yeah, these are bitwise operations, and they're going to be very helpful for us. Now I'm going to show you how, okay, a little bit more. Okay, so what happens if now, instead of dealing with just like individual bits, if now all of a sudden we're dealing with entire like numbers? So let's look at that. So if we say, let's say we have 0, well, let's say this, or that. Okay. If it's not bits, but like entire numbers, then we just go bit by bit. So we say, so this is going to be 1, and then 1, and 1, and 1, and 0, and 1. So OR just takes like every bit and then ORs it with the other bits. Okay, so now let's try doing like 1 0 1 1 1 1 with and with 1 0 0 0 1 1. Okay, can you guys put in the chat what you think this is? Cool. Okay, looks like most of us are getting it. So yeah, so we just check. Okay, is this bit set and is this bit set? Yes. Okay, is this and this? No. Is this and this? No. Is this and this? No. Is this and this? Yes. Is this and this? Yes. So therefore, boom, correct answer. In C++, or really in C and in most languages, the way you write out and or and not and XOR is with these symbols right here. So moving forward, all ands will be this ampersand, or will be this vertical line, not will be a tilde, and XOR will be the caret. Okay, and I'm going to talk about one more bitwise operation, which is very important. That is bit shift, which looks like this. So a bit shift, it takes in some number, and let's say we bit shift it over by, let's make that. If we bit shift it over maybe by 2, then it will take whatever this number is, and then it'll just add 2 zeros to it, to the front. Or if we go and shift it this way, let's just shift it 1, then it will remove that number of zeros. So yeah, if we have like some slightly more complicated number and bit shift this over by I don't know, 3, then you just take this and go 1, 2, 3. And if we bit shift this by 3 as well, then we take this and take 1, 2, 3. So really you can think of like the number like sliding along. So like if we have a number, so 1, 2, 3, 4, 1, 2, 3, 4. So if we have like a 1 right here, and then we shift this way by 2, then it will end up being this, because it'll be shifted over 1 and then 2. But then if we like shift it back maybe 3, then it will become 0, 0, 0, 0, 0, 1, 0, 0. Or if we, I don't know, shift it this way again. So really what I want to express to you is that this shift like can like just moves whatever the content is and it like moves it over. But a problem with it is, okay, so now what happens if we try to shift it over by like 8? Okay, so we take this number, and okay, so we say, so 1, 2, 3, 4, 5, 6, 7, 8. So that's how many zeros got added to the front. But look at this. So here's like where our number is right now. And like these bits are being lost because we're like pushing them too far. And if they're being pushed too far, then we just forget about them. So therefore, like we had this number, we had this 1 here, and then we shifted over. Maybe we wanted it in like that bit instead. And then we shifted back over here. But then we ended up shifting it too far in this case to now we've like completely lost this data. And maybe that's what you were looking for, but it's just very important to know like how big of a number you're dealing with, or like how much space you're dealing with. So you don't like accidentally shift your bit around too much to where you lose data that you weren't expecting to. So yeah, so this brings me to my next topic, which is declaring numbers with a certain size. So in C++ and C, it is generally best to always declare your numbers with this syntax. And this says, so I want an integer with 8 bits. And unsigned means just always make it positive. So for example, so we might say like an unsigned integer x equals, and we can say 0b to mean binary. And now we put 8 bits. So we put 1, 2, 3, 4, 1, 2, 3, 4. And then in here, we can maybe set like this bit to 1, and maybe set this bit to 1. I don't know, maybe we want a different number right here, so y. So, but this is 16 bits because of right here. So we would need to make this 16 bits. Boom. But this is really helpful, mainly because of bit shifts and knowing like, okay, like how much can I shift it over? So this is like a brand new way of thinking about C and C++. It's in terms of like how big or how long your numbers can be, how big they are stored in your RAM. Like, yeah, because this number is actually taking up like this much space in your RAM. It's taking up 8 bits. if you were to go and pull out your RAM stick and be like, oh yes, look right there, that is where these 8 bits are being taken up by this integer X, or like, oh, this is the 16 bits that are taken up by this integer Y. Yeah, so right here, so you should use hex and binary notation to declare numbers, like right here. And hex notation is when we put a 0x, and binary notation is when we put a 0b. And another side note is whenever you have a bunch of preceding zeros in a number, so if you have like this, so look how many zeros there are here. We don't really care about all these zeros, so we can actually just leave these all off, and it can clean up your code a little bit if you do that. Or if you want to keep it very clear, it's like, oh yes, 16 bits, so I'm declaring every single bit, including all the preceding zeros. It can be good to declare it in this way. It's up to your personal preference, but I usually remove those first bits. Another thing in C++, it is always best to just always use unsigned numbers, because you don't have to worry about accidentally like making your number negative. Especially if like you only want to deal with positive numbers, it's better to just only deal with positive numbers by declaring it as unsigned. And if you declare it as unsigned, then now the amount of numbers that you gain access to actually goes up. Is unsigned essentially absolute value? Basically. So, okay, sorry if this doesn't make sense to everyone, but I want to show you really the difference between signed and unsigned. So if we have a signed int t, the greatest number that we can actually write with signed int t is 7f, which I believe is 127 in decimal. And the reason for that is because if we were to write this out in binary, so 0, 1, 1, 1, and 1, 1, 1, 1, this very first bit is considered like the plus or minus sign. It's the sign bit. So if we go and we set this to 1, now all of a sudden this number, it becomes negative. So we lose out on an entire bit. That's like saying like, all right, like I'm allowing you to have a 3-digit number, except actually I'm taking away one of those digits. And you're like, wait, but like I wanted to go up to like 999, but now you're taking away one of those digits for just the negative sign. Like that kind of sucks. So so the first bit is just like the negative sign. And you'll learn more about it in ECE 15a. But yeah, all you need to think about now is just make everything unsigned, so that now all of a sudden you have access to this number, so that now you can go all the way up to FF, which is 255. Okay, good. Yeah, so go and download the exercise. And there's 2 files in it. And there are like 4 different functions to implement. It's using these bitwise operations. You're going to be using a lot of bit shifts. Yeah, I wish you look. It's kind of fun to like do this for the first time. You have to like think through it. And down here, I have posted a solution that I made up. And if you do not have a C++ compiler, then I posted a link to an online compiler. So you can just download the file and paste the code in here and then edit the code in here. And then when you're done, just save the file so that you have it for later.